Today we have two eminent guests from Rapid2 Technologies Private Limited. They are a dedicated blockchain company. They are a company who are into blockchain, and I hope they will talk about their company and what are the range of projects which they are into. And we were lucky enough to collaborate with them for the last 2 years. We have been interacting with them in different verticals, like students, some of our students were there and they supported them to pursue their projects. And we, as a faculty, we were also involved with them and we did some kind of projects and so on. So we have been exchanging knowledge for the last 3 to 4 years, particularly in the domain of blockchain technologies. So in continuation to it, we wanted them to handle this session where we felt they are the apt people in Chennai to deliver about blockchain technology. Okay, that is the prelude upon which we have invited them to come here and give a talk on blockchain technology. And it's up to you. You have to leverage this properly. They are from industry, and you have to do your coding, do your questions. You can try to extract the maximum of knowledge or information from it. So, I am happy to introduce Mr. Mohan Raj Polur Babu. With over 20 years of IT experience, Mohan Raj excels as an innovator and advocate, challenging conventional thinking with relentless focusing on delivering new, innovative and valuable solutions to customers through reimagined propositions and experiences. He holds a postgraduate degree in computer applications and he is also a PMI certified project management professional. Also, he is a speaker of the HIMSS Middle East UAE Health Week 2017 conference on blockchain for healthcare. He has co-authored papers on off-chain smart contracts and connected health submitted for the advanced workshop on blockchain technology organized by IIT Bombay. He has effectively equipped high-ranking bureaucrats with the necessary technological skills through NISG program to excel in their roles. As a visiting faculty at ICISA, he conducts blockchain training for international auditors, including the esteemed Comptroller and Auditor General of India. He has fostered industry-academia relations and regularly hosted workshops and webinars and many more. His interests are in building decentralized networks and P2P computing platforms, designing solutions that leverage blockchain, IoT, and AI technologies, helping companies navigate the ever-changing landscape of technology and create a lasting competitive advantage. Driven by evolving market demands, his new interests are machine unlearning, I'm reading it right there.
Model to model transfer.
Model to model transfer and exploring their potential applications. Currently, he is the Vice President at Rapid2 Digital Solutions. As a VP and technical strategist, his role is pivotal in influencing the organization's bottom line. By leveraging his expertise and insights, he develops and executes strategic plans that align technology initiatives with business objectives, driving efficiency, innovation, and profitability. His ability to identify and capitalize on emerging technologies, coupled with his business acumen, enables him to make strategic decisions that directly impact the organization's financial performance and overall success. And last but not least, he is also an ACM professional member since 2018. And he will be covering sessions on solidity of Ethereum platform. Right? So this is a summary of the speaker whom we have here. And we have another speaker. I am equally excited to invite Mr. Balaji Ramnath. Balaji Ramnath brings a wealth of knowledge and experience to the table with nearly 17 years of IT experience. Put together, they have about 38 years of experience. Ranging from the early days of mainframe systems to the forefront of cutting-edge generative AI. He has proven exceptionally tech-savvy, continuously exploring various technologies. Among, among its their vast array of technological exploration, his deep dive into the realm of blockchain stands out prominently. This exploration has been fueled by his unwavering passion for data and security. As he recognizes the transformative potential of blockchain in these domains. Balaji has a deep understanding and practical experience in implementing blockchain solutions. He can promptly enlighten on blockchain technologies, intricacies, and potential applications. In addition to his extensive experience as a blockchain architect, he also deeply understands the tools and technologies that guide successful blockchain implementation. His proficiency in Ethereum, Hyperledger Fabric, CODA, IPFS empowers him to architect cutting-edge blockchain solutions tailored to the specific needs of diverse industries. His broad knowledge of these tools and practical expertise make him a valuable resource in guiding organizations towards effective and secure blockchain adoption. With a proven track record of successful implementation, he is a trusted advisor and an influential voice in his organization. So this is the profile of the speakers whom we have here. So I mean, I have rendered the profile. To make use of the profile depends on you. All the best. Thank you, sir.
So this is a result of the questionnaire. Of course, like you're not able to see it, it's a little brightened there. So the first question was, what are your primary goals for attending this session? So most of you have mentioned that learning the latest advancements in blockchain as one of the things that you wanted to cover up. And then followed by understanding the fundamentals and exploring the potential use cases. So definitely like we'll be just going through. Gaining insights into Ethereum and Solidity, I feel like you're not so much interested in it. Maybe because it's too technical. I mean, there are different flavors of blockchain, right? So first, once you understand what blockchain is, then it'll be easier for you to navigate through the blockchain ecosystem itself. Of course, I understand that, but we will just try to cover more of the interest that you have. And Ethereum, I'll just try to minimize it. But of course, it is going to be a kind of a lab session. Of course, it might be of interest to you when we actually do the lab. So that's we will cover that in the second session. And the second question is, what is the level of familiarity with blockchain that you have? So most of you have said like you're beginner, and yeah, so we are going to start with the introduction of blockchain and slowly take you through the journey and make you aware of what's happening, what's most prominent things that are happening in the blockchain world, and then we take you to the use cases part of it. So from a beginner, definitely, if not advanced, you will be in an intermediate level after taking this session. That's for sure. And the third is, how would you describe the technical background? Yeah, most of you are familiar from a technical perspective. I would say like 60-40%. There are a few of you who are in non-technical. So only the second session could be non-technical. The first session, which is introduction to blockchain, it will cover some of the core concepts of cryptography and all like. And that's the only technical part of it. And yeah, so hopefully this session is aligned with what your interests are. That is what I just want to validate, and it's good. So without taking much time, I'll just hand it over to Balaji, who will be taking the first session, which is introduction to blockchain. Okay, over to you, Balaji.
Thank you, Mohan. So as part of this agenda, we will be covering like the evolution of blockchain. Then we will going to be talk about the digital currency. So what are the digital currencies that are currently available in the market? From Bitcoin, Ethereum. Then we will go in depth of like how Bitcoin and Ethereum plays a major role in the blockchain technology. So we will discuss about those details. And second thing will be like we will have an in-depth view of what is blockchain, the basics behind the blockchain technology, and what are distribution ledger technologies, and what are the models that will be supporting the distributed ledger technologies. That detailed explanation is something like we will look at as part of the next session. And like the third and fourth part will be like what are the blockchain detailing, like what is the block, what are the details that are available in the block, what are hashing technologies. Then we will talk about the digital signatures, how the data or transactions will get passed in the data blocks, what are smart contracts. So, and then we will see like how the transactions are generated and what are the various algorithms that are used in the process. So we will talk about each and every topics in detail. We'll get a bit of fair understanding of each of those as we go into the details. Then finally, like we are going to talk about the Ethereum and the consensus algorithm that we will be using for the data transmission in Ethereum, and what are the smart contracts and what is the side chains. So this is in depth on the whole what we are going to talk about in this session, and this will be at a basic level. So we will start with the introduction now. Yeah. So evolution of blockchain. So cryptocurrencies are used in the blockchain's growth list of records to verify the transactions using distributed ledgers. And as each transaction is immutable and distributed ledgers can't be tampered with, industries across the standard are started to use the blockchain to automatically verify, validate, and process transaction in a safe and secure network using smart contracts. So a blockchain technology is something like immutable and it is distributed ledgers. So immutable is nothing but you cannot change the contents of a blockchain. So whatever transaction that you pass in the network, it is immutable. And it is passed across the distributed ledgers. Say like there is a network connectivity and there are 5 people in the network and they are going to generate a transaction and share it across the network. So that will be a distributed ledger. And each ledger, the copy that each of the person will receive will be the same replica. So say like if I am going to save the transaction details of a customer, this customer has a account detail in this, he is going to transfer an amount of 10,000 to a person B. So this is what my basic transaction will be. That information will be sent across the network in blockchain technology. Suppose like there are 5 people in the network, all 5 of them will receive this same copy of data, stating like this is the customer who is going to transact with the customer B, the amount that he is going to transact will be 10,000. So now 5 of us, right, in the network, who are in the network are aware this is what the transaction is going to happen. So the main advantage of blockchain technology is that this data that sent across the network will not be changed by any instance because it is encrypted using the digital signatures. Then we are hashing it using the hashing algorithm. It will have its own public private key concepts. I will explain those in detail. So because of all these things, nobody can crack what the details that are present in the blocks. So end to end, when a customer sends through the network, so only the people from A to B will know the content of it. Rest of the people in the group, right, that people will know only the hashing, what key has been passed. They will not know what is the actual information that has been passed in the transaction. Got it? That is the key advantage. As you see, like introduction of Hyperledger project enable businesses to transform their networks and processes in a decentralized and distributed applications. So this depiction gives us like how blockchain technology evolved itself. So starting with blockchain 1.0 in way back in 2009, it was started using the Bitcoin. So it was introduced and it was used across the cryptocurrencies, digital payment system and financial transactions. And the evolution of 2.0 is in the year 2013, smart contracts were introduced where the evolution of Ethereum also happened with a 3-tier architecture. And then in blockchain 3.0, it is the decentralized applications, DApps. That's what we call as DApps. So decentralized storage, front end to enable business and blockchain of things. So all these emerged as part of the blockchain 3.0. And finally, like blockchain 4.0 is the upcoming future. So it is in persistence. So that will be across the industry 4.0. We have it across the automation, ERP, SCM, IoT, collaboration with artificial intelligence and machine learning. So this is the basic evaluation of how the blockchain has transformed itself from the initial beginning till where are we today. Yeah. So digital currencies. So as you already know, like the normal fiat currencies are dollars, pounds and rupees. So normally people used to transact using those dollars, pounds and rupees. Like if I want to give 1,000 rupees to another person, I will hand it over using the rupees. So that is pretty much the fiat currencies that we are talking about. In a digital currency, what is the digital currencies are like? So Bitcoin, Ethereum, Litecoin, Ripple and Monero. So digital currencies are very much similar to fiat currencies which can be used for the purpose of trading, investment and exchange. Due to its digital nature, it can be easily transactable instantaneously and across the border in a secured way. So like how we transact, right, using the bank accounts. We send money through the bank accounts, like using the Bitcoin also we can use the transactions possible across anywhere in the world. Digital currencies are introduced to overcome government regulators such as central banks and government run financial institutions to ensure stability of its market and price without any political or social influence. And mainly digital currencies run on a blockchain platform to ensure transparency, security and immutability. So it is transparent. As I told you, like every people in the network will know what is exactly happening. They will have each copy of it. Security, as you know, like it has been hashed. We have the public key private key concept. So it cannot be hacked by any of the hackers unless and until you know that key, nobody can see the transaction that is happening in the network. Immutability, as I said, like nobody can change it. So 5 of us are there. If somebody is trying to tamper the data, okay, assume that they are able to crack that key. So by cracking that key, they will be able to alter the data that is transacting in the network. If that happens, immediately an alert will go to each of the person in the network. So everybody will get an alert that a person is trying to change it, and everybody will know like it has been tampered, so they will directly reject it. So that way, like a new block will be prevented from getting added. So the data will be intact. So that is the main advantage of the Bitcoin. So 3.0, like as I said, like it is related to the decentralized application. It is nothing but a computer application that runs on a distributed computing system. DApps have been mostly popularized by distributed ledger technologies, named the Ethereum blockchain, where DApps are often referred to as smart contracts. So this is the Ethereum client architecture that you see here. So user via the UI interface app, he will interact with the web3.js node, and you have the DApps client. Then you have the individual DApps. So these are the blockchains. So as you see in the second diagram, so this is the ASP.NET application architecture that is currently in existence. So we will have a front end layer, and then we will have the middleware ASP.NET application, and in the end we will store that information in a database. So this is the regular architecture that we currently have for all applications that are running. That is the decentralized application architecture based on the blockchain technology. So if you see there, we again will have the front end part of it, the web browsers. If you see the database, it will be stored in the blocks. As I said, like all the details will be stored in the blocks. So if you see here, there are 3 nodes. 3 nodes are interconnected with each blocks. It is purely based on the blockchain, and you have something called smart contracts. Smart contracts are nothing but an additional piece of code that can be embedded in a blockchain, which will execute certain set of contracts. Say like as I said, A transmits amount to B, right? So in that case, they can additionally do some validations and say like this interest amount has to go to B. So that small piece of logic will be incorporated in the blockchain, and it will also get executed along with the transaction. So that is what a smart contract is all about. So on the whole, like this is the DApp part of it. Yeah. So from Bitcoin to Ethereum, so how things evolved starting from Bitcoin. So cryptocurrency in early 1980s, when David Chaum invented a blinding algorithm that remains central to modern web-based encryption. So in 1980s, this person called David Chaum, he invented a blinding algorithm that acts as a base till now for all the algorithms that we use in the blockchain technologies. So the algorithm allowed for secure, unalterable information exchanges between parties. So it was so secure that the information that is passed cannot be cracked at any point of time. Then later in 1980s, Chaum introduced something called DigiCash. On top of what he has discovered, he has come up with a new strategy like DigiCash, which is a profit company that produce units of currency based on the same blinding algorithm. Unlike Bitcoin and most of other cryptographies, DigiCash control wasn't decentralized. So since it wasn't decentralized, we couldn't move further with that DigiCash in the market. So shortly after that, Nick Szabo developed and released a cryptocurrency called Bitgold, which was notable for the using of blockchain system that underpins most of modern cryptocurrencies. So before the blockchain, before the Bitcoin and Ethereum's evolution, we had this Bitgold. Then after that, even before the Bitcoin virtual currencies, we have the conventional way of transacting, which is nothing but your GPay and Paytm that we are using in the apps to make the payments, right? So those evolved. And then finally, in the year 2009, a person called Satoshi Nakamoto. So his existence is still now like it's a mirage. So like this person actually found something called Bitcoin. So Bitcoin is nothing but it's a decentralized currency which was used to transaction between peer to peer from user to user. We enable that transactions to happen. And it was an open source system and nearly like 2.9 to 5.9 million people today have a Bitcoin wallet. So this is a huge amount and it keeps growing. And Ethereum was introduced by Vitalik Buterin as a white paper. He was also part of the initial Bitcoin magazine. In 2013, Buterin wanted Bitcoin to be built on a decentralized platform. So what they did is like with the like-minded technocrats like Gavin Wood, Ethereum virtual machine was written and introduced in the market in 2014. And it was open source for several other cryptocurrencies to be launched from Ethereum platform. So starting with early 1980s, we had this blinding algorithm, then we had the DigiCash, then we had this Bitgold, then the evaluation of Paytm, GPays, Google Pays, then the evaluation of Bitcoin, then in the year 2013, we had the evolution of Ethereum. So this is how from Bitcoin to Ethereum we have come this far. So quiz time, you can just scan this, you will have a couple of questions appearing on your screen, try to answer those. So we will continue here. What is blockchain? So we will go through the basics of blockchain. So blockchain is a self-sustaining peer-to-peer database technology for managing and recording transactions with no intermediary involvement. So this is the main point, intermediary involvement. Say like if you're going to transact from one place to another or a person to person, you want an intervention of a middleman like bank. So in order, bank will maintain all the transactions, whatever you send. So that involvement of middleman is completely removed in the blockchain technology. So that is one key aspect of it. Because blockchain verification is handled through algorithms and consensus among multiple computers, the system is presumed immune to tampering, fraud and political control. So as I said, like people in the network will have a copy of each and every transaction that is being sent, right? So suppose like there are any changes to it, each and every person will receive that alert saying like there is a tampering that is getting happened, right? So that way like they will know like people are trying to crack the thing. So they will not agree to it. So they will directly reject whatever the update that is getting happened for the transaction. So that is why it is presumed immune to tampering. So no fraud can happen in this case. Then it is designed to protect against domination of the network by any single computer or a group of computers. Participants are relatively anonymous, identified only by pseudonyms, and every transaction can be relied on. So anybody can be part of that network. So since it is hashed using the public key, private key, we have that encryption protections with the algorithms that are getting used. So it is safe and secure. Moreover, like because every core transaction is processed just once in one shared electronic ledger, blockchain reduces the redundancy and delays the existence in today's system. So since we are sharing it across multiple people, we don't have to send it over and again to each and every people. It actually prevents that redundancy. So as you see in the other diagrams, like whatever that we saw in the points, it is that same. It is distributed. It is transparent. So without consensus, nothing happens in the people, the network, the people will have to consent together. So that is the main point of it. It is immutable. You cannot change the data what is being sent in the network. And then we have the provenance. It is highly regulatory compliance. So these are the key features of blockchain basics. Distributed ledger technologies. Yeah, so distributed ledger is a type of database spread across multiple sites, regions or participants. It removes middlemen from the business transactions used by enterprises to process, validate and authenticate transactions or other type of data exchanges. So as you see here, this is a centralized technology where everything converges to a central person. So he will have the complete ownership of whatever that is getting transferred. So that is part of the centralized technology. Then you have the decentralized. So decentralized, at each and every node you still have the controlling people. But in distributed, it is distributed across. So there is no middleman or somebody to control whatever that is happening over the network. So that is what the decentralized distributed part of it. So how it works? The transaction distributed among all nodes. So as I already told you, like whatever transaction that we will be sending in blocks, the blockchain, it will be distributed across all the nodes. So validator validates the transaction and reaches a consensus among the participants. So there are 5 people in the network. So they send out a transaction to each and every block. So everybody will receive the same set of transactions. Everybody will validate it. Say like, yes, I agree to this transaction. Everybody provides their consensus. Only then the block will be added to the blockchain. Got it? Once consensus is reached, new set of transactions are added to the ledger. So once it is added, again it will be reflected for all the people in the network. So whatever new blocks that get added will be visible to all the people in the network. So that is how distributed ledger works. See, I'm saying like I have 10,000 rupees, I'm transacting it to A to B. Now again B wanted to send something to C. Okay. So B will send, suppose like A has initially 10,000 rupees. He sends it to B. Now A again wants to send another 10,000 to C. But initial or total amount that A had is only 10,000. Now he is still trying to send another 10,000 to C, which does not exist in real world. Correct? So that time the transaction will be sent to each and every person in the network saying A is sending 10,000 again to C. But everybody will know initial amount of A and B. A has 10,000, B had 0. A sent 10,000, now B had 10,000, A had 0. Now A is again trying to send 10,000 to C, which is not a possibility, right? So everybody will know A now currently hold only 0 amount. So since he is trying to add a new transaction, it will not update the existing transaction. It will be a new transaction that A is trying to send to C. Now everybody is aware of the concept like A doesn't have any amount with them. They will reject the transaction. So it will not get added to the block. Got the point? That's how it works. See, it is a network, right? So in the network, I have 5 people, right? So A sends to B is a transaction. So that blockchain is consisting of blocks, right? So each and every block will have information. What is the person? A, B. And what is the initial amount they had? 10,000 and 0. Now what is the transaction that is happening? A is trying to send 10,000 to B. This information is completely available in each blocks. And each person will have the same information. Got it? A, B, all the details. Who is the sender? Who is the receiver? What is the initial amount he had? What is the amount that is getting transacted now? It is visible to all the people in the network. So by that way, you will know like what is happening in a specific transaction. You will have the transparency. So suppose like that, as I give you an example, A is trying to send another amount to C, which will not be the case because he doesn't have any amount left in his bank. That's how it is. Yeah, moving on. So we'll look at the distributed ledger technology models. So we have the blockchain, which is what we will be concentrating on. There are other models that are also available. So one specific model is Tangle, which is direct acyclic graph. So mostly IoTs, Internet of Things, use this model Tangle. So Tangle is a blockless, scalable, lightweight distributed ledger. It is a directed acyclic graph. It is just like a web with 0 blocks. Each web consists of different nodes which work in depth. Each node carries a weight. So that's how it transacts. and limitless scalability and data growth, and it is less prone to attacks and forks. Similarly, we have another model called Hashgraph. Again, it is a DAG, which is directed acyclic graph. It uses two special techniques to achieve fast, fair, and secure consensus, which are gossip about gossip and virtual voting. So these two are other models that are available. And blockchain, as we already saw, these are the key features. It works based on the peer-to-peer distributed database, and then it is across the distributed ledgers. The transaction gets passed on, and each block contains a hash, timestamp, and transaction. We'll get into that.
How this Tangle model is used by IoT?
In IoT, actually, you're going to capture the data that is coming from different IoT devices, right? And then you're going to feed into a network where the data is going to be recorded. We are not talking about immutable. We are not talking about any other concepts that is there in blockchain. But we are only talking about the distributed system, right? So you get the data from one IoT device, and you get the data from another IoT device, and data needs to propagate to multiple devices, and there will be regular logics that will be written to validate the effect of that data, right? So here it works on a gossip protocol, wherein like there won't be a validation, or there won't be kind of mining that will happen. The data will be just sent into the network, and there it just collects all the data, and the validation happens inside that. Not like a blockchain thing. It is a totally a different algorithm that is used. That is what we call it as a directed acyclic graph, and it works on gossip protocol. Even this hash graph is also very much similar to that. The reason why we are talking about these two models is one of the challenges that we face in blockchain is it may take a longer time to validate a transaction. But in case if it is coming from the devices, we need not, in certain cases, we need not validate because it is only coming from the device. It is free from manipulations done by the human involvement there, right? So in those cases, the consensus will be different, right? And only in blockchain, we need this kind of consensus model and all that. So our focus area is blockchain now. That is what industry is following for all the financial or all, there are a lot of other use cases which I'll be talking about later in the session. So blockchain is being followed. Tangle and Hashgraph primarily like there is an blockchain model called IOTA. Okay, they use this Tangle. Okay, similarly Hashgraph is also used by not a blockchain model. Sorry, it's a decentralized or distributed system, which is using IOTA uses Tangle, and similarly Hashgraph is also used by a few of the similar kind of products and protocols. In the Tangle model, there is a different logic that it happens. It is only, there is no security. You need not validate because the data is coming from the machines, right? Only if you program a machine to send a fault data, it will be sending a fault data. But the data once out of the machine, right? It comes out of the machine, you would not be able to modify it, right? It is just an IoT device. I'm talking about not machine or IoT devices like that, right? So maybe a Raspberry Pi, which is sending, you connected it to a container wherein you wanted to measure the temperature of the, goods that are carried in the container, right? So it is just going to stream the data. Continuously, it is going to stream the data. There, if you are going to put a blockchain in place, right? You need to go through all these consensus models and protocols and all like, and then it gets into the actual system. By the time you get an indication that there is some fault that is happening, it would have already caused more damage to it, right? We need a lesser protocol there, or not a heavy weight on the consensus, but we want the data, right? So for that reasons, like they use Tangle for those kind of implementation and systems and all that. We can implement checkpoints, right? We can just have the data is encrypted and sent out, and it is tagged to that particular device or the machine which is sending the data. Those kind of protections we can implement still there. But again, like as we increase the level of security or the protections, right? There is a lot of executions that will happen, which may little bit reduce the performance of it. If it is within the acceptable grade, it is always good to go with that, right? Yeah. You had one question.
Blockless in terms of Tangle?
What is blockchain in terms of Tangle?
There is no blocks. In blockchain, you create a block. A block is, say, if you're recording a data in the database, right? You're going to store the data in rows and column format, right? Now in blockchain, you call it as a block. There is no rows and column, columns and all. It is all blocks that it will be containing the data. And in case of Tangle and all, there is no concept of block. In blockchain, a block consists of transaction, and there are a lot of other attributes that are associated with the transaction in order to make it secure, right? That block nature is not there in Tangle. That is why it is called as blockless. Okay.
So this is how transaction is processed in a distributed ledger technology. The transaction is initiated in the first place, as you see there. Okay. So it is encrypted transaction. So you cannot see that actually. Then you have the smart contract which passes the transaction based on the rules defined on the network. So there can be small piece of code which works on the transactions to generate it, encrypt it, it will pass on to the network. Then every transaction is represented in a block. So that is the block that you see there. Once that block is created, each block record is distributed to all the participants on the network. So it is getting passed to all the participants. Now the participants will validate the block and they will provide their consensus. That is what you see here. So transaction, once each and every person in the network says like I'm okay with this transaction, they will consensus. So then once that is done, the block gets added here. You see here. Now the blocks get added to this chain. Right. So now you see that block. So this is the content of a block. So block at the top XYZ, it's the block number. Okay. Then you have the previous hash. Okay. Previous hash, it means like the previous block's hash number will be there. Then you have a timestamp attached to it. Then hash of the current block, which is the transaction. Then you have something called nonce. Then you have the actual transaction attributes. Nonce is nothing but it is a integer. Okay. So it is a combination of nonce and the actual transaction which will generate the hash for that specific block. That's how it works. So nonce is a integer value. It will, along with the transaction in the block, it will be a combination. It will create a 256-bit hash value. So that will get generated for each and every block as you try to add it into the blockchain. So this is an example of like how the transaction happens and what exactly happens in that block. So we will look at that. So now this example is like we wanted to create a campaign to raise a fund. What exactly happens in the process, how the blocks get generated for each and every action that we are trying to perform here. Okay. So initially, the service provider will authorize the participants. So he will decide like who will be the participant for this fundraising campaign. Then he creates a campaign. So in that case, a block gets created with a number, for example, 456. And you will have the hash value, timestamp, and the transaction will be set fund, fundraiser, the benefit model and goal. So these are the details of this block. Now what will happen is this nonce will generate a new hash value for this block. That will become the previous hash value for the next block. Got it? So for this create campaign transaction, this is how a block gets generated. Now the third one is validate. The service provider will validate the campaign once it is getting created. Now if you see, this block has a different number, 468. The previous block had a number of 456. Okay. So in this block, the previous hash will be the hash value of 456. Okay. So that will be stored in 468 block. It will have its own timestamp value, and the nonce will now create a new hash value for this block based on the transaction and the actual transaction and the previous hashing. Now this transaction has a update valid flag. Yeah, as I was talking about, now after creating a campaign, we will validate the campaign. That is again done by the service provider. So we will have something called update valid flag that will be set once the validation happens. and those details will be stored in this specific block. Okay. So after that, now once we have validated the block, once we have validated the campaign, they will invite the funders. So that is the next step. So for that, we are not creating any new blocks. Then the bidding for funding is open now. Once the funder bids for it, that is when we will create the next block, stating like the funder information will be updated with the amount what is trying to bid, what will be the balance amount. So those details will be stored in this block. So that is what bidding for funds. Then we have this accept funding. So once bidder has proposed this part, now we have to either the fundraiser has to accept it or reject it. Now he will go ahead and accept it, and the flag will get updated. So once that is done, another new block is getting created, and we are updating that close flag here in this process. Now, after closing everything, now the transaction is triggered. Yes, so now after everything is approved, now the financial institution, he triggers this transaction. So basically that amount from financial institution will get transferred to the customer institution, where the fundraiser will be studying. So in this case, a new block gets created with the new nonce, new hash values, and the transaction initiated flag for that funder is updated. Yeah. So after that, the funds are received by the customer institution. Then the campaigns get executed. The executable flag is set in a new block. Then finally, commitments are delivered, stating like the return flag to the funder has been set appropriately. That will again be a new block. Validate closure. So now the service provider will validate, saying like all the funds have been transmitted from the financial institution, the customer institution, and he closes out the transaction. So all these blocks will be connected in the network. Each and every step, you know, like how the block gets generated, how the hash value gets generated, and how the current hash value for the block gets created based on the nonce and the transaction. So that's how the new hash value will get generated. What are the actual transaction details that are getting stored in each and every block? The transaction varies. It is not the same transaction, right? Initial example I said like A transfers amount to B. That will be the same throughout the network. But here, each and every block, you have different transactions. So here, the update flag is updated, validate flag is updated. The previous it is executable flag. Next is transaction exit flag. So for each and every transaction, your hash value keeps changing. It is not going to be the same transaction that is transferred, right? So as and when your transaction changes, your hash value also. So now like we saw like how it happened. So this is permission, secure, transparent, privacy is always there, unlinkable identity, auditability. So at any point of time, you know what is there in the network. It is because it is transparent to each and everyone in the network. Then you have the append only, automatic processing, built-in validations, reduced. So suppose like there is an existing transaction that already went. Now if you wanted to update something, again a new block gets created, not updating the existing transaction in that existing block. That's how blockchain works. Got it, right? Yeah, so this is the flow we saw. So each and every block has an individual unique block numbers for each and every transaction. So the hash value also varies for each and every block that is in the blockchain. So each and everywhere, what are the flags that gets updated, and in the end, the validate flag also gets updated to close the campaign. Yeah, so this is another example that we have shown with the animation, small animation. So this is again the fundraiser concept. Let me show you how it works. So now initially the create campaign is the transaction that gets generated. So in this node, the transaction will be create campaign. That is the first one. Now a block gets created, okay, and the hash value is there. Transaction is create campaign. Nonce and hash of the transaction. So this is how it gets created. So now this nonce is the key value. As I said, it is an integer value. and the hash of the transaction is this one. Now this node has identified that specific combination. So this will become the hash key for that block. See? So this becomes the hash key. It is like in the group there are somebody called miners. Okay, so in a blockchain technology there are people called miners who will be there. Their work is to identify that hash value along with the nonce. So once they identify the hash value and the nonce, there are various algorithm strategies that are there to identify that. So once they identify, they will send it in the group stating for this transaction I have identified this nonce and hash value. Once they publish it, everybody will look at it, they will validate that, and that nonce value should be lesser than the hash of the next block. Otherwise, it will reject that. Say like in this, the hash value is 1, 2, 3, 4, 5. So if you see the next block's hash will be something like 1, 2, 3, 4, 6, for example. If I am going to generate a hash of 1, 2, 3, 4, 7, it will reject it because it is greater than the hash value of my next block. So unless and until the miner is able to identify that hash value which is lesser than the next block, it won't allow them to add it to the blockchain. So this person, this miner has identified it. Now the consensus among the group is got in the way, everybody agrees to it and the block gets added. So that will be the hash value and the nonce value for that specific block. Okay. So now after this, so that's why you see OK in all the blocks. That is, everybody is OK with that. They are providing their consensus. That is when your block gets added in the blockchain. So after that, we are creating a campaign, then validating a campaign. So if you see the transaction details, this is what it is there. So we have the fundraiser, the CIN, the fund amount, model, funder balance, and method is create. So this is what will be the actual content in that block, but it will not be visible to the external world because it is hashed based on that hash key and the nonce. That's how it is. So next will be the validate campaign. So again, like the miners will do their job to identify the hash value based on the nonce. So now this specific miner has identified that, and that goes in for a consensus among rest of the group. Once they are okay, another block will be created for validate campaign. So hash value is generated for the validate campaign. Now everybody is in consensus with that, and that block gets added in the blockchain. This is what it is in the actual data. So now the method from create, it has become validate. Rest of the values remains intact in the transaction. Now next is the fund campaign. So once validation has happened, now we have to fund it, right? So the funder has to fund it. So in that case, again, the nonce and hash value will be generated, and the miner will identify that based on the values. Now this specific node has identified that. Now that becomes the key for the third block, and everybody, it is sent for consensus for everybody in the group. Once everybody is okay with that, this funder is the one who has provided that fund, and what is the balance amount in his ledger, and the method is update. So this transaction will be stored in the third block, and a new hash will be created, which is what we are seeing in the screen. So these are the examples that we have spoke about till now. So let's have a small quiz. Let's just try it out.
Yeah, 25 responses, 2 responses are from our side. Okay. So, so the first question, the answer, 17 of you had mentioned the correct answer, which is 2013. That's when the first white paper was published. Okay, first white paper was published on smart contract. Actually, it was from Vitalik Buterin, who co-founded Ethereum. Okay, before that it was all Bitcoin, and Bitcoin, there wasn't any smart contract, or basically it had a contract which will work only for the cryptocurrencies. Then they came up with an idea on why not we create a code which also gets included in the blockchain as the data that is included in it, right? And the code should be immutable and it should be consensus based and all that. And that's how like the smart contract came into picture with Ethereum. Okay, anyway, I don't want to take your time now. You can just respond back and then I'll just we'll go through this responses. So the first question we discussed, it's 2013. Is Google Pay is a form of digital currency? Actually, when we talk about currency and when we talk about digital currency, Google Pay is not that, right? Do you know what is the reason or what is the digital currency that India has? Recently, government has launched that. Anyone? It's called e-Rupee. Okay. If you have bank accounts, probably like you would have got an invite from the bank accounts for you to participate in that digital currency program, wherein you will have the exact denominations, okay, with the serial number of currencies. Those are nothing but it's backed up by the blockchain with all the hashes and serial numbers encrypted, encoded, and all that. Okay. So, yep. Most of you provided the correct answer. Who invented Bitcoin? It is Satoshi Nakamoto. Some of you had said David Shum and Vitalik Buterin. See, these people, right? Vitalik Buterin, Gavin Wood, all were like, they were inspired by Bitcoin. Okay. And then they started off, why not we just look at this digital currency from a different aspect? Why it should only try to satisfy the currency problems? Why can't it satisfy other world problems, right? So that's how like they looked at it, and what they came up with is Ethereum now. So these are the results of our first quiz. It's good. Most of you cleared that. At least I would say like 17 of you, all across the questions, you provided the right answers. So let's see how this quiz went. The second quiz, probably when we start the third quiz, we'll look at the result of second quiz.
So we'll continue here with the blockchain in detail. Building blocks. So like we have already discussed about this, so we will just have a in-depth view of it. So consensus, like as we say, like once the blocks are generated, we have to get the consensus from each and every member as part of that network, right? So member nodes in a blockchain network use a consensus protocol to agree on ledger content and the cryptographic hashes and digital signatures to ensure the integrity of transactions. So that is what it is. And cryptographic hashes. So cryptographic hashes such as like SHA-256. So that is the current algorithm which has been picked up by Bitcoin, SHA-256. So it is a 256 bit value that gets generated for each and every block based on this algorithm. Ensures that any alteration to transaction input, even the most minuscule change, results in a different hash value being computed, which indicates potentially compromised transaction input. So as I said, like when somebody tries to intervene your block, that minute change will also generate a different hash value. So assume that there are around 100 blocks in a network. Okay. So each block will have its own information validated by the people in the network, got their consensus and has been added in the blockchain. Now, a person or a traitor is trying to hack it. So assume that he has cracked one of the blocks. He is able to identify that specific block's hash value. Okay. Now the problem is he has to not only hack that specific block, but all the blocks he has to get the hash value to get that information. It is not just one specific block. If I am able to crack the hash value of one specific block, I cannot see the content of it. I have to ensure that I do a complete hashing of all the blocks. That is when I will be able to see that value. That is the biggest drawback for any ethical hacker who is trying to hack them. It consumes enormous electricity because it is not a very simple task to hack a 256-bit value. And that too, like hacking one specific block itself will consume enormous amount of days and days of time. If he is going to do that, think that there are 100 blocks. He has to still crack 99 more blocks to do that, which is unrealistic and not possible in the real world scenario. So that's how it is so very conservative and it is so very secured. So that is what it is, cryptographic hashes. And then we have the digital signatures. So this is to ensure that the transaction originated from sender, signed with private keys and not imposters. So there are two persons, say A to B. So A is trying to transact to B, right? So in this case, there is something called public key and private key, as I already told you. So what happens is, using that specific private key, person A will encrypt the content of what he is trying to send and a hash value gets generated. That will be sent across the network. Now he will make sure that the destination party knows the public key. Okay. So that person and this person only will be aware of that public private key combination. So rest of the people who are trying to look at it will not know that key at all. Okay. Everything is in the digital form, nothing is written anywhere. Okay. So the person B will be able to decrypt that data using that public key. He will have his own private key. So both of them will have their own private keys, but a common public key. So the person in the destination should have to provide that public key, then only the hash value will match. You will be able to see the content of that transaction. That is how it works, the digital signature. Then you have the smart contracts. So as I already told you, smart contracts are nothing but a small piece of code that are written on top of the blockchain. So assume like there are few examples down the line, we will see like how smart contracts are written there. As of now, like just think about it as a small piece of code. On top of it, it will automatically get executed. Okay, so for that any specific transaction where you set that smart contract, and it will also be encrypted and it will be available only for the persons who are transacting between you. That comes, it is upcoming. Yeah, so these are some of the properties of the hash codes. So in simple terms, hashing means taking an input string of any length and giving an output of a fixed length. So you type whatever you want, the output will be a 256 byte key. You can type a number of paragraphs or you can type only 2 words, still the output will be a 256 bit key. So these are some of the characteristics of the hashing. So it is deterministic quick computation, free image resistance, small changes in the input changes the hash key value, collusion resistant and puzzle friendly. So the examples that you see here are some of the algorithms of it. First one is MD5, that is one algorithm. It produces a 128-bit hash. Collusion resistance was broken after 2 is to the power of 21 hashes. So somebody has cracked this algorithm after computing it for 2 power of 21 times actually. And the next one was SHA1, produces 160-bit hash. Collusion resistance broke after 2 power 61 hashes. And the next is SHA256. So this is the one that is currently used by Bitcoin. So till now, like there is no such instances of collusion resistance that has happened. So it will generate a 256-bit hash as I told you. And the next is KCAC256, which again produces a 256-bit hash and it is currently used by Ethereum. So these last two are the ones that are being currently used by Bitcoin and Ethereum for hashing techniques. Yeah, so this is one example. Okay. Yeah. So creating and verifying a digital signature. So now assume that we have a sender and a receiver. Okay. Assume you are going to send a draft of a contract to a lawyer in another town. You want to give your lawyer the assurance that it was unchanged from what you sent and that is really sent from you. So authenticity should be there and the contents of the document should also not change. So we must ensure that it happens. So you copy and paste the contract into an email. So it is a digital contract that we are trying to send it across to a lawyer. Using special software, you obtain a message hash for the contract. So in the left side diagram, for that document, we are generating that hash. So this is the hash value. Then you are encrypting that hash using the digital signature. So I have created a hash value. Now on top of it, I will be encrypting that using my public key, private and public key combination. So the private key will be unique to me, and I will generate that public key and I will send it to my lawyer. Now my lawyer will have his own private key. Unless and until he uses that private key, he will not be able to log into the network. And using that specific public key, he will be able to read the contents of the contract which I am trying to send it to. So it is a combination of private and public keys. So as you see here, now in the initial phase, we have created that hash code, encrypt the hash code with the private key of the sender. So creation of the digitally signed document from the sender has been created after that process. So now you are sending the digital document. Now it again recalculates the hash code. Now he will have that hash code. He will decrypt the signature with the public key of the sender. So the sender will send him the public key. Using that public key, he already has a private key which allows him to log into the network. Using it is a combination of both private key and public key, he will be able to validate the document and receive it. And he will also know the authenticity of it, like who sent the document, because that public key has been sent by the sender himself, not anyone else. So that's how he validates and makes sure that authenticity is maintained. Yeah. So we were talking about the smart contracts. So it is nothing but a small agreement between two parties. That is the smart contract. So smart contracts are computer programs that are not only enforces an agreed upon performance between two parties, but the code itself explains the obligation of the parties, unlike in many traditional contracts. So it is an understanding between two parties, like what has to be done for that specific transaction that they are performing over the network. Smart contracts facilitates business arrangements without the formality and cost associated with the traditional route. Smart contracts is a more cost effective and efficient way of defining an agreement. So in a real time world, like we have to prepare the stamp papers, we have to create everything for sender, receiver, we have to declare all the terms and conditions. There can be so many annexures and everything. It is a time consuming as well as cost consuming one in the real time scenario. So smart contracts will provide an effective and efficient way of doing that. That's what it is. So smart contract can be written in many different languages like Java, Golang, Solidity. So these things hands on we will be seeing in the later part, in the second half of it. So we'll get an in-depth understanding of those languages. So this is the traditional way of execution, definition and audit controls. Everything will involve manual way of creating a contract. Now since everything has become digital and smart, we are having all these easy to define, it is easily executable. One thing it is like once the digital contract is executed, it is executed, that's it. You can't do anything about it. Then you have the audit control. So each and everything is logged in the network. So at any point of time, I can trace back till 20 years back, I can know like what happened to that specific contract in the network. So that level of information will be readily available. Yeah. So this is one specific another example like how the transaction is generated by automated and manual sources. So we have a producer who has to transmit some of his products to the end customer. So what happens in the process is what we are going to see now. So using the IoT, he is going to transmit whatever that he is going to do to the distributor. Then we have the logistics that come in place. From distributor, it takes up this product and send it to retailer. From retailer, we will ship it to customers. So at various point of time, we will have that every transaction stored in a block in a blockchain. And the right side part of it, the code that you see there, so these are various information that we are storing in the block. So first thing is the time of arrival. So when the transaction arrived at what spot, and company's identity key. So what is the identity key of that producer? Then each and every item will have its own identity key. Whatever item that he is going to transport, that will still have an identity key. So that identity key is also stored as part of the block. Then we have the temperature deviation. So initially what will be the temperature of that specific item. So that is also getting captured. And what is the spoilage condition? So item can be damaged in via whenever we are transmitting it from one place to another, there can be wear and tear happening to that package, right? So in that case, what is the spoilage? We have conditions of that specific item. So that is termed identified in a spoilage flag. Then what is the departure time and weather conditions? So this is a small piece of code which is nothing but your smart contract. So on top of the blockchain, this piece of code will run and it will make sure to capture all these inputs. It will be stored in the block and it will be transmitted to each and every parties in the blockchain. So the producer, IoT, distributor, logistics, retailer, consumer will have their own copies with all these inputs fed at each level. So say like when the producer is sending, the spoilage flag will be set to no. After logistics, it will be going to retailer. Now he validates everything. He identifies one of the packages damaged. So he will set that, he will say like this is damaged, right? So he will set that spoilage flag to be yes. So he is providing that consensus to everybody because he has received it in a damaged way. So then everybody will agree to it. He will capture a photo and send it across and everybody will agree to it that it is damaged. So likewise, like we can able to track at each and every spot. That is the main usage of blockchain in a secured way. This was recently implemented in Walmart retailer in US. So they were also very concerned that some of their packages were getting returned very often. So they wanted to identify like what was the reason behind that. So they have implemented this blockchain technology at various levels as I have explained, and they identified that when they are carrying their packages from warehouse till the retailer, there were spillages or spoilages or damages happening in that case, and they were able to scrutinize and identify a specific problem and they have a solution in place. So that's how blockchain is put into use, right? So once the smart contracts are executed, then this is what happens. The actual data with that algorithm SHA-256, we are hashing that using the private key of the sender. Then the digital signatures are validated and public key is also there. So together we are creating the content of that packet, of that block. From a receiver standpoint, he has to still log in using his private key. He will know the hash value. Using the public key, he will have to provide that public key which has been provided by the sender. If the public key matches, he will be able to see the content of the block. Otherwise, it will straight away reject. He will not be able to see that. That's what you see here. And also like it is shared across, it's a shared ledger. As I said, told you, like it will be shared across multiple people. The content will be the same. Nobody can tamper it or do whatsoever. That's what you see. So producer ledger, distributor ledger and consumer ledger. So at each and every spot, the ledger contents are the same. Temperature, location, time, weather conditions, spoil flag and package detail. So this is what we saw in the smart contract. So that same data is retained at every node. That is what the intent of. Okay. Types of blockchain. Yeah. So we have two types of blockchains. One is the public blockchain and another is the private blockchain. So public blockchain protocols based on proof of work, consensus algorithms are open source and not permission. Anyone can participate without any permission. So the data will be transmitted across the network. Anybody can actually participate in it without any restriction. Like it is open to everybody, but they cannot view the data. They can just participate. As I told you, like there are minors, right? So proof of work, there is one concept called proof of work. I'll come to that later. I'll tell you what is that. So from a public blockchain perspective, like everybody can participate in that blockchain concept. So examples are Bitcoin, Ethereum, Monero, Dash, Litecoin and Dogecoin. Effects are like potential to disrupt current business models through disintermediation, no infrastructure costs, no need to maintain servers or system admins, radically reduces the cost of creating and running decentralized applications. The main difference between the public and private blockchain is only restricted to a certain group of people. So we can decide like who can view the contents or who needs to be part of the network. Not everybody can participate in that network. So that is the private blockchain. So that is what it is. So for example, consider a private equity company. By definition, a private equity is not a publicly traded on stock exchange, and its investors are typically ventures, capital firms, private equity firms, or angel investors. The participants in this network need to be known and have credibility in capital to invest to be able to participate in the blockchain. So only people who are part of that private equity firm can be part of it, because it is related to the stock and other capital information related to their company, so it cannot be exposed easily to the public. So it will be restricted to a few group of people who are working as part of that private organization. So they create a private blockchain in this case. The examples are Monax and multi-chain. FX will be reduces transaction costs and data redundancies, replaces legacy systems, simplifying document handling, getting rid of semi-manual compliance mechanisms. In that sense, it can be seen as an equivalent to SAP in the 1990s, reducing the cost but not disruptive. So this is a pictorial representation of what is the difference that we saw in the previous slide. So same thing, the registration, smart contract preparation, blockchain manipulation and cost. So at various, what are the difference between the public and private? And there are one more type, which is nothing but federated blockchains or consortium blockchain. So federated blockchains operate under a leadership of a group. As opposed to public blockchains, they don't allow any person with access to the internet to participate in the process of verifying transactions. So there will be a group of people governing it. 3 to 4 people will have the authority or ownership to decide who should be part of that specific blockchain group. So that specific blockchain is called federated blockchain. It's not owned by one person, it will be a group of people, 4 to 5 people who will own the ownership of it. Got it? So that is what the intent of it. Examples are like R3 banks, EWF Energy, V3I Insurance and Coda. And the effects is like reduces transaction cost, data redundancy, replaces legacy systems, simplifying document handling, and getting rid of semi-manual compliance mechanism. So these are similar advantages that we saw in the previous slide for the private blockchain. In that sense, it can be seen as equivalent to SAP 90s, reducing the cost, but not. Yes, that's what I said. So private will be owned by one set of person. One person will be at the top. He decides like who should be part of that network. But in federative, it is a group of people. So that group can be consisting of 4 to 5 people who will be like top persons, who will have the authorization to know or decide who should be part of that group. So it is governed by one person in private, but it is governed by a group of 4 to 5 people. That is the difference.
How is it decentralized if there is a central point of control like a person or a group in private and consortium?
That's a good question, right? So how it is decentralized if you have someone who is the gatekeeper of that network, right? So in a public blockchain, anyone can participate, right? In a private blockchain, there is a gatekeeper who allows only certain organizations, certain parties to participate in it. So when you take the blockchain to the industries, right, they don't want to expose the entire blockchain network to all the group outside on a public network. Okay, if it is currency, we can understand because it is going to be used by all the citizens, all the people. So it can be on a public network. But if for industries, right, say if I'm a manufacturer, right, and I may have multiple vendors supplying goods to me, and I will have multiple customers to whom I supply goods to them, right? I can build a blockchain network wherein I can send the invoices, purchase orders, everything in a digitized format, secured format, and distribute in this network. And I wanted only my vendors and my customers to be part of the network. Because if I bring in all other parties into the network, it's basically I'm exposing my business data to outside world, right? So industries wanted a blockchain platform where they can have a control over it. Now, when we say control, they would not be able to manipulate. They would not be able to release any code without the consensus of all the parties. Nothing they can do it. Only thing that they can do is they can say, okay, this member can be part of the network, and they can just look at the data that is there in the network. That's it. They are only acting as a gatekeeper. All other properties of the blockchain is preserved in the private blockchain and also in the federated blockchain. That answers your question. And before we go to the next set of things, right? It's already 10:15, but we started 15 minutes late, so I'll just take few more minutes. In that period, I wanted to go through the website. So there is a dedicated website which simulates a blockchain system. Okay, you can just go to that website, and you can also feed in your data and try to understand how blockchain works. So this is Anders Brownberg. Okay, got that. Right. You're able to see this, right? So this is just an illustration of blockchain, right? We were all this time Balaji was talking about the components that makes the blockchain. Now we will just go through each of this component, and we'll see like how it plays a vital role in establishing the blockchain network. So the first of it is hash. How many of you know what a hash is? You're in cryptography. Yeah, please go ahead. What an hash is? So we can just see the functioning of hash. Can anyone say where hash is being used? Where all it is being used? Digital signatures, yes. Then encryption, yep. Anywhere else? ATM machines. Maybe I'm not aware of, maybe. So for me, right, the first time I was introduced to hash was when I started downloading videos from internet or softwares from internet. When you download huge size files from internet, right, for protection, they would say like you have an MDA5 hash code or certain hash codes, right? What is the purpose of that hash code? Can anyone tell?
Hash codes that are provided with the software verify the identity of the publisher.
Verifying the identity of the publisher, it's an indirect way, but the direct thing that it does is once you download a 400 MB file or a 500 MB file, okay, you need to be sure that the content of the file is intact. It is not being hacked, or it is not having some data which is going to spoil your system, right? So the publisher who is going to upload that file also provides an hash code. So when you download the file, again you run through the hashing algorithm on that file and see what is the output hash code. If the output matches to what the publisher has provided, it means whatever file that you have received is correct, right? And if it doesn't, then it means the file has been manipulated. Right? That's what hash is. So now here you can see an example, SHA-256 hash. So in this, I'm just going to see this is an empty. There is no data. Even when the data is not there, there is an hash to indicate an emptiness, right? And if I'm going to type a data here, say ACM program. You can see like as I keep typing this, right? You can see the values of the hash keeps changing, right? And whatever I type, the number of digits that are there in the hash remains the same, right? This is what the hash is, right? This hash is uniquely identifies that particular data set. Theoretically, it may not be the case when you see, because if you're feeding a book, it provides a hash. It can provide a hash. So your book is having 1 billion characters, and it is just going to provide 64 characters or 32 characters or 48 characters. Now the question would be obvious, right? How can 1 million characters match to a 48 characters or 32 characters and all that, right? So definitely there would be a conflict that can occur where a hash can match to two different, content, right? That is what we call it as collision in cryptographic terminology and all that, right? So till now, practically, with SHA-256 and SHA-512, these are secured algorithms. There is no collision identified. Okay, and prior to that, we had SHA-128, and there are a lot of other encryptions. Collisions were identified, and as and when like the collisions are identified, then they just ignore that and look for the better algorithm and all. Like, we don't know when we enter into the quantum world, or when quantum takes its dominance, then probably like this can also be proven wrong. There can be, in fact, like that can attribute to much more efficient algorithms, right? So this is what hash is all about. So you understood what an hash is. Now this data, you're going to store it in a blockchain, in a block, and there is a hash that is generated for that. So if you are trying to change the data, the hash of it changes. Okay? Right. Now we'll look at what is a block. The next tab takes you there. So you have a block. The block number is 1. There is a nonce. Okay, nonce is just a number for now. Just consider it as a number. And there is a data and there is a hash. Okay. So I'm just going to provide the same data here. ACM program at SSM. Right? You have the hash, you have a nonce, and you have a block. If you see, the color is not coming up here. In my screen, the color changes to pink. Okay, what it means is the hash doesn't match to this data. Okay, the reason for that is the hash that is currently there is not only for this particular data, but also it considers the nonce. Okay, so we need to mine it to get a new hash. This new hash is nothing but a combination of the block number, nonce, data, all three things put together, a new hash gets generated. Okay, so that is what the hash is now. So if someone is going to store a block into the blockchain, right, it's going to carry the block number, and there will be a data, there will be hash, and there will be a nonce set for it. Okay. Now, if you see the hash, you can see something peculiar in this, right? There are 4 zeros prefixed to it. The reason for that is the block is going to sit into a blockchain, and that blockchain network has defined a rule that all the hashes of the blocks should start with 4 zeros. Okay. Now I will come to the point on nonce. See, we know like if you are just taking this data, going to hash, and if you're going to paste it, you're just going to get this DC, phi, EA and all like. This is the thing, right? Now this doesn't have any 4 zeros as a prefix, right? If this block goes into the network will reject this block because it doesn't satisfy the rule of the blockchain network, right? So now you're going to go to the create a block. You're going to put the same data here, okay? And if you just remove the block and the number, it will match to what was there, DC, phi, EA, you can see, right? What was there in the first screen, you got it. Now there will be a block number attached to it. Now we need to find a number, a nonce, such that the resultant hash has 4 zeros. Right? We know a hash is generated out of some content. We have a content, but we wanted a hash with 4 zeros. So to that content, we need to add something so that the result hash comes with 4 zeros. And that is what mining is all about. Okay. So now you can see like there are 4 zeros. The number is 25163. Right? This is what miners do in a blockchain network. In a proof of work, a consensus method, all the miners will compete with each other to find a nonce which, when added to the data, gives an hash that matches to the rules of the network. Okay. So now we got a block. The miner has successfully created a block, and then this block goes and sits into a blockchain. You can see there are multiple blocks here. Block number 1, block number 2, 3, 4, and there are nonce. And in fact, on my screen, all these are in green color. It means like the hash matches to the data set that is there. Now in this, the data set is, all the blocks data are empty. But for computing the hash, it will consider the block number and also the nonce. Okay. So with that, we have the hash which starts with 0, 0, 0. You can look at the first block. For the first block, the previous hash value was just zeros. Okay. In blockchain, we call this as Genesis block. The next block, you can see like there is the previous hash is nothing but hash of the previous block. Okay, it starts with 401578. If you look at the block number 1, you can also see the hash 401578, right? So what does it resemble like? Can anyone? Sorry? No, what does it resemble like? What this structure resembles? Linked list. It is nothing but the linked list, right? In a linked list, you take the previous value of the previous data set and put it here, right? So it's the same thing that is there, right? It is a link. It's kind of a linked list, right? You take the previous value, previous hash value, put it into the into this block, right? Now, if I'm going to add a value, of course, because of this color problem, you would not be able to see this. This is green in color, okay? The block number 5. If I'm going to say ACM, type it, it's pink on my screen. It goes pink or red in color. What it means is the hash value that is generated is not matching to the, it doesn't go with the rule of the network, 4 zeros. That is first thing. And hash doesn't even match the data there, right? So if I'm going to change the value, then, thank you, I need to mine this. Okay. So what happens? The miner, this mining is like basically it's a computational intensive algorithm which the miner uses, and it goes sequentially, like right from he just puts a value of 1, 2, 3 and all that, and finally he comes to a value here which is 100, almost like 111,424, right? 1,11,424 is the nonce number. So he would be running that algorithm to find this nonce number of the number and all that, right? So now it is very easy, right? If you go to the last block, if you can change the value, you have to remine, you get the value. But what happens if you're going to change the value, say in the second block? The second block becomes red, pink in color. Okay. And the second values, second block's hash is copied out to the third block, right? The third block also becomes pink. That is what it is in my screen. Just believe me, it is not there. It is here. And similarly, if you go to the fourth block, it also turns pink. Fifth turns, everything goes off. Because none of this follows the rule of the network. All this, if you see, like none of this starts with 4 zeros. All these blocks gets invalidated. So if someone goes to a prior block and modifies a value, then every block subsequent to that block goes invalidated. Right? So now what he has to do? He has to mine it. He has to go to that second block, he has to mine it, and then he has to, now the second block's hash value will be copied here, and again he has to mine because its hash value is also not, starts with 0, 0, 0. So he will mine here, and then he will just again come to the fourth block, mine it, right? And fifth block, he has to mine it. Okay, by the time he comes to the fifth block, say, if there is another block which is added, then he has to also go there and mine it, right? Like this, he has to continue it. Now there is a difficulty. You agree that there is a difficulty in remining and getting it, right? Now to make it much more complex, you will see this distributed thing. So this blockchain is in peer A, and it is also there in peer B. It is also there in peer C, right? There are 3 nodes which are having the same blockchain, the same content, the same data and all that. No, if it is changed, it's a rule. How do you know like it is changed? You're changing the data, right? So the miner is not going to read the data. The miner will not be reading like what is the transaction that you made to an A, or what was the transaction that happened between A to B. He's going to only look at the hash value of the transaction, right? So if the transaction changes, hash value changes, right? That's where like miner get notified that there is a change that occurred. He's not going to read the data into it, right? That answers your question. See, you're saying, I go to the blockchain, right? And I'm just going to change the value, the data here in the second block. Okay, I'm going to change it as ACM, right? Now what happens? The hash changes for this value because I introduced a new value. The hash value changes. Since the hash value doesn't meet the rule of the network, it just becomes red. Yes, the previous value also gets changed. It's because I'm just going to tamper it, right? If I'm going to tamper it, the hash gets generated. The next block hash, which is pointing to the previous block, will also get changed. If the next block doesn't get changed, can't we just identify that since the values are not matching to each other, right? So now what will happen? Okay, now this 2 blocks goes off. Now what will happen to the 4th block? The 4th block will be green in that case, right? Because the 4th block carries the previous hash value. Right, the previous hash value doesn't is B93EF, right? That is, it is not modified. So your blockchain, your second and third block alone will be in red color, will be flagged, but your 4th block will not be flagged if you don't apply that 40 rule, right? Because you are just copying what is there in the previous, and the previous hash did not change here. So that by that way, like it just keeps. It will become green and therefore it will not be validated. Right. So that is where it is difficult to generate a hash with 4 zeros in beginning. Okay. Now if you go to the real world blockchain network, it is not 4 zeros. It goes of 8 zeros, 16 zeros and all like. It becomes more computationally intensive to generate it. That's where like miners use GPUs, not a normal CPU, but GPUs to do this. Okay, and it requires heavy power. Okay, now going to the distributor. So we know like there is a difficulty there, right? If it is one blockchain. Now in a distributed network, you have the same blockchain replicated across different nodes. So you have peer A, then peer B, peer C, right? Now if I'm going to change here in ACM, right? So we know like all subsequent blocks will get invalidated and it is all in pink color on my screen. Okay. If you go to the next, right, you will see like this value doesn't match with the previous blockchain's value. Basically like the blockchain that I may be having a node and you may be having a node, right? My node has different set of blocks and your node will be having different set of blocks. We will never come to an agreement at all in the new block that is getting created. Right? So, if a person wanted to manipulate it, he has to mine this block, the first peer block, and not only that, he has to also go to the next blockchain, introduce the same change, right? He had made a change in the first blockchain as ACM, right? He has to go to this blockchain, in that particular block, block number 2, he has to introduce that change, and again, like he has to remine it here. Okay, and remine the subsequent blocks. Not only that, he has to go to the 3rd peer. He has to type in the same change that he made, and he has to again remine everything. Now, how difficult it is, right? So this is the fundamental. This is the principle behind the proof of work consensus method, which is being followed by Bitcoin, and most of the blockchain networks that we have initially followed proof of work. Okay, and this is a very good model, but it has its drawback. So when you make it more computationally intensive, right, you need more power to compute the nodes, and also it requires more time to compute the nodes. right? The transaction performance degrades. Basically, initially, probably like when the number of miners will be less, you will be, when you start the network, probably like your complex, you would have put in complexity of 4 zeros. But as the network grows, you wanted to make it more difficult because there will be more number of miners, right? So you will introduce 8 zeros, 16 zeros, and to calculate the nonce for getting that 16 zeros or 8 zeros is going to be taking longer time as well and longer GPU. So power is wasted. So we are talking about go green, right? That is something that is which is happening across the world. We talk about ESG and all that. So it doesn't contribute to that. Not only that, the transaction performance, if you take Visa and all, like I think it is 4,000 transactions per second is what like Visa work at, if I'm right. Okay. But you would not be able to achieve that level of transaction performance in blockchain. If that doesn't happen, then the blockchain will not be suitable for currency, right? So that's where there are multiple other consensus methods that came in. Okay. So Balaji was talking about different components and he stopped at the consensus. So Balaji, you can just start from consensus.
Consensus, like we were talking about the proof of work. I think Mohan was explaining the proof of work. So miners, when they try to generate that hash using the nonce value, right? So those people are called miners who are trying to crack that combination. And the process of doing that is called proof of work. So miners can be part of any network and their job is to do this. So they will have to work on that using the combination of neons and new hash keys. They will try to generate a new hash key matching that specific block and will try to do the mining for it. So hash rate determines like likely a participant is to add the next block of transactions to the blockchain. So the intent of doing is that like once they crack it, so they will send it across the group of people in that network saying like they have identified the hash value for that specific block. Once everybody has a consensus over it, they will add that as a new block at the end of the chain. So that is what the intent of it. So miners work to solve a puzzle consisting of a mathematical function called hash along with specific properties, extremely repetitive and therefore computationally expensive. So not normal CPU, they will require GPUs to do that and it will take months and months of effort to crack it. We just saw an example of just generating simply using an algorithm which is straightforward. But as Mohan said, like computational effort with 6 digits of zeros or 8 digits of zeros, it will take much more effort to crack that, in reality, which is impossible to do that. So it will consume enormous effort, enormous electricity in doing it. But there are miners who are doing it, but it will take enormous effort. That's what the point is. An attacker should possess huge computational power, at least more than half of total network hash rate, such that they could mine block after block, winning the proof of work competition time after time. So that's what it is. Proof of stake. Proof of stake is similar to what proof of work is. It is taken care in the Ethereum part. So each network node is linked to an address, and the more coins or tokens that the address holds, the more likely it is that they will mine the next block. So they will collect something called coins or tokens in this process, which will be used to mine the next block. So an attacker who wants to make a fraudulent transaction would need over 50% of coins or tokens to process the required transaction reliably. So buying these would push the prices up and make such an endeavor prohibitively expensive. So in both the scenarios, it requires enormous effort to do it, and as well it is much more expensive than what it is really looking like. So this is one fine example of the consensus, the Byzantine generals problem. So there were a group of generals, okay. So each commanding a part of Byzantine army has surrounded an enemy city. So to attack the city, all generals have to agree on a battle plan. So generals can communicate via messengers only. So each of them have surrounded a city. So the plan is to attack that city, but they are coming in from different directions, but they don't have any form of communication to do that. So they have to inform each of the groups saying this is what the time is when we are planning to attack, and everybody should be on the same consensus to attack them, right? So let's see like what are the problems that are there in doing so. So the messengers might be captured by the enemy and the message might never reach the other general. So that is one possibility. So one person, he has to go all the way manually to the other group stating like we are planning to attack the city by 10 PM. assume that they are planned to attack the city by 10 p.m. So he has to go in person to the next group to inform them this message. But in between, there is a possibility that he might get captured by the enemy city, right? So in that case, the message will not get transmitted. The difficulty in the agreements is that one or more generals might be traitors and are interested in sabotaging the battle plan. So there can be traitors in other groups as well who doesn't want to attack the city. They will be part of the city, who will be working for the city, but as a traitors in this group. So if you go and tell them the message that we are planning to attack the city by 10 p.m., there are chances he might tweak the message and say like 11 p.m. or a well ahead time. So that way, like, he is trying to protect the city because he is a traitor. So that message communication will not happen in the proper way. To end this, they might send false messages, distort messages, or not send any messages at all. So there are three possibilities that we being a traitor can do. All loyal generals will act according to the plan. A small number of traitors should not cause the loyal generals to adopt a bad plan. So this is what the scenario, real-time scenario that can happen. So what is that we can do is, a client sends a request to invoke a service operation to the primary multicast the request to the backups, replicas execute the request and send a reply to the client. So then the client waits for the 3f plus 1 replies from different replicas with the same result. This is of the result of the operation. So he will wait for the multiple responses from each of the person. So he will validate to see like whether he is in consent with it. So in the previous example itself, we had a scenario like where the generals, they have to go and tell them the timing. So assume that initially one person, he says like he is agreeing to it that 10 p.m. is what they are going to do, and he has to take 2 hours to validate and resend it that he is in compliance with it. So he will again fetch it and he will go to the next group. So then again that person will again take the 2 hours to evaluate it and he will give us consensus. So totally it has taken 4 hours for completing 2 consensus. Then the third person, assume he is a traitor, now he is going to either manipulate the message or he is not going to send the message at all, right? So if he is not going to send the message at all, he is going to reply it right away and send it. So the fourth person will know the first 2 persons have taken 2 hours of time, the third person has either taken it a short time or he will be manipulating the message such that it takes more than 3 hours. So that way he will know the third person is a traitor and the first 2 message are legitimate. So that's how they will validate. So the fourth person will know like whose message is invalid. So in that case, he will also put in a 2 hours for that. He will pass it on. So the fifth person will also be on the same consensus that 3 persons have agreed with the 2 hours. So he will also go with the same 2 hours rather than that 5 hours. Thank you guys. So if you still have any questions, you can always reach back.